Module 5 Failure Theories. Before going to the details of the different theories of failure, we'll discuss another one important factor called factor of safety. Also called FOS. What is factor of safety? Till now we have seen about strength of the material. What are the different kinds of strength? There is a yield strength we have denoted by sigma y or Sy, and we have seen the ultimate tensile strength SUT, and also we have seen different kinds of stresses which come in member due to different kinds of loading, mainly normal stress, shear stress, bending stress, torsional stress, etc. When we design a component, there are a lot of uncertainties to be accounted for. Basically, the uncertainties arise due to uncertainty in the magnitude of force, magnitude of external force is uncertain, uncertainty in the material property, inhomogeneity in the material, residual stress in the material, variation in dimension of the component, and due to assumptions made in the analysis. And various other factors. To account for these uncertainties, we use a factor called the factor of safety, which is defined as nothing but factor of safety, usually denoted as N, is nothing but the failure stress or strength of the material to the allowable stress. Allowable stress is a stress value which is used in design to determine the dimension of the component. It is considered as a stress which the designer expects will not be exceeded under normal operating conditions. And we have seen ductile materials. For ductile materials, factor of safety is given as the yield strength divided by allowable stress. Or I can write allowable stress is equal to yield strength of the material divided by factor of safety for ductile materials. Similarly, for brittle materials, since they don't have a well-defined yield point, there the design is based on the ultimate tensile strength of the material, and the factor of safety is given as the ultimate tensile strength divided by allowable stress. Or we can write allowable stress sigma allow is equal to SUT divided by N for brittle materials, where Sy is the yield strength of the material and SUT is the ultimate tensile strength of the material. There is a use of factor of safety, and what factor of safety to be used depends on the application, depends on the material conditions, etc. For different application we use different values of factor of safety. And also it has to consider the safety of the component. That is, if the component is used where safety is a very important criteria, then we should go for a very high factor of safety. And when the factor of safety becomes high, normally the dimension of the component becomes high, and the weight of the component also becomes high. So this is one important parameter which we have to optimize in many of the design conditions. That is, if we choose a high factor of safety, naturally it will go for a higher weight of the component. And if you want to reduce the weight of the component, you have to go for lesser factor of safety. So this is there's a trade-off between the factor of safety and the weight of the component. Failure theories. The failure theories are developed in order to help us to design the component to withstand the load. As we have seen in the previous modules, the mechanical materials can be classified into two. Mechanical materials are classified into two, basically ductile materials and brittle materials. This we have seen in the earlier modules, and we have also seen that ductile materials are those materials whose percentage of elongation is more than 5%, and if the percentage of elongation is less than 5%, we call those materials as brittle materials. And the failure theories have been developed for the both materials, ductile materials and brittle materials. For ductile materials, the failure of the material takes place by yielding phenomena. So yielding is a criteria for failure for ductile materials. So different failure theories are derived for the ductile materials. Basically, the maximum shear stress theory, or it's also called Tresca or Guess theory. Then we have distortion energy theory. It's also called von Mises-Henke. Then we have the maximum strain energy theory. Maximum strain energy theory is also known as Haig's theory. Also called Haig's theory. Then we have ductile Coulomb theory. Also called TCM theory. Similarly, for brittle materials, we have another set of the failure criteria. And for brittle materials, the failure takes place by fracture. So it's a fracture criteria for failure. Fracture is the criteria for failure for brittle materials. And different criteria of failure are maximum normal stress theory, also called Rankine theory. Then we have brittle Coulomb theory. BCM. Then we have maximum normal strain theory. Also called Saint-Venant's theory. And we have modified Moore theory. These are the different failure criteria for the ductile and brittle materials. For ductile materials, we have the maximum shear stress, distortion energy theory, and maximum strain energy theory, and the ductile Coulomb theory. For brittle materials, we have maximum normal stress, brittle Coulomb, maximum normal strain, and the modified Moore theory. For ductile materials, the major theories will be the maximum shear stress theory and the distortion energy theory. And for brittle materials, the major one is the maximum normal stress theory. The other theories are just some small modifications of the existing theories. So now we will see the different failure criteria in detail. Maximum shear stress theory or Tresca or Guess theory. So this is Tresca or Guess theory. Okay. The maximum shear stress theory predicts that yielding begins when the maximum shear stress in the component equals or exceeds the maximum shear stress in a tensile test specimen of the same material when the specimen begins to yield. So here you can see we are talking about two stresses. One is the maximum shear stress in the component, and another one is maximum shear stress in a tensile test specimen. Suppose we have a body with a state of stress such that we have principal stresses sigma 1, sigma 2 and sigma 3 are in such a way that sigma 1 is greater than sigma 2, greater than sigma 3. If this is the principal stress, we have seen the maximum shear stress tau max is nothing but sigma 1 minus sigma 3 by 2. This is the maximum shear stress coming in a component whose principal stresses are sigma 1, sigma 2 and sigma 3. So this is the first stress. I'll make it number 1. So second stress what we are talking is about the maximum shear stress in a tensile test specimen. In a tensile test specimen, we know there is only a uniaxial loading. So we can say that sigma 1 is nothing but equal to sigma 2 is equal to 0, sigma 3 is equal to 0. So we have only one principal stress, that is nothing but the stress in the direction of loading. So in a tensile test specimen, what will be the maximum shear stress? This is nothing but again sigma 1 minus sigma 3 by 2, or that is equal to sigma by 2. And at yield point, what will be the maximum shear strength? So this I can call it as yield shear strength of the material. This is nothing but sigma by 2. And what will be the sigma value at yield point? It will be yield strength of the material. So we have seen that in the previous model, we have seen that the stress corresponding to the yield point is called the yield strength of the material. So we can say from here that yield shear strength of the material, or this I denote as Sy, is nothing but Sy by 2. This yield shear strength is equal to yield strength by 2. This is a it's an important criteria coming out of this MSS theory. Now this is the second stress. Now what does this theory say? Says that the maximum shear stress in the component, that is this stress, should not exceed the maximum shear stress in a tensile test specimen. That is, this stress should not exceed this stress. So what will be the condition for design? It will be the maximum shear stress, that is sigma 1 minus sigma 3 by 2 should be less than or equal to Sy by 2. This will be the criteria for design. Or we can write sigma 1 minus sigma 3 should be less than or equal to Sy. And when we put it in design equation, we can write it including the factor of safety. We can write it as sigma 1 minus sigma 3 is equal to Sy by n, where n is the factor of safety. N is called the factor of safety. This is about the maximum shear stress theory. Now, if we consider a plane stress element, which is having stresses sigma, suppose a plane stress element, having two stresses, basically sigma A and sigma B. So for this case, we can say that the first principal stress is equal to sigma A, second principal stress is equal to sigma B, and third principal stress is equal to 0. Now, there are 6 conditions in which the principal stresses can be arranged. One will be So for this kind of a system, sigma A and sigma B, the first principal stress sigma 1 is equal to sigma A, sigma 2 is equal to sigma B, and sigma 3 will not be there. Now, these stresses can be arranged in 6 conditions such as sigma A greater than sigma B greater than 0, or sigma A can be greater than 0 greater than sigma B, or 0 greater than sigma A greater than sigma B, or sigma B greater than sigma A greater than 0, or sigma B greater than 0 greater than sigma A, 0 greater than sigma B greater than sigma A. So these are different conditions in which the 3 principal stress can be arranged. And what will be the criteria for each arrangement of the principal stress? That is for condition 1. What will be my criteria? Maximum shear stress should be less than the yield strength. Maximum shear stress is nothing but sigma A by 2 should be less than or equal to Sy by 2. My condition is sigma A should be less than Sy. For second condition, the tau max is equal to sigma A minus sigma B by 2 should be less than or equal to Sy. So the condition will be sigma A minus sigma B should be less than Sy. For third case, tau max will be minus sigma B by 2 should be less than or equal to Sy, or we can say sigma B should be greater than minus Sy. Fourth condition is tau max will be sigma B by 2 should be less than or equal to Sy. So sigma B, Sy by 2. So sigma B less than or equal to Sy. Fifth will be maximum shear stress is equal to sigma B minus sigma A by 2 should be less than or equal to Sy by 2, or we get sigma B minus sigma A should be less than or equal to Sy. Finally, for condition 6, we can write minus sigma A by 2 will be the maximum shear stress should be less than or equal to Sy by 2. We can write sigma A should be greater than or equal to Sy. So, now we have got the 6 conditions for failure by MSS theory. Now, if we plot this on a graph, how will it look like? Okay, now we'll try to plot this in a sigma A, sigma B graph shown here. Now, condition 1 is sigma A should be less than Sy. So that we can draw it as a line here. This will be Sy. This will be the first line. I'll make it condition 1. Second one is sigma A minus sigma B should be less than Sy. So that will be sigma A minus sigma B less than Sy should be a line like this. This will be condition 2. For condition 3, we have sigma b should be greater than minus sy. So it should be in this side. From here it should be this side. Here it should be this side. From here it should be this side. Similarly, condition 4 is sigma b should be less than sy. So that will be this line. And similarly, the criteria 5 will be shown here. And finally, the last criteria 6 will be shown here. That is, if my stress in the component is within this polygon, then I am in the safe zone. So that is the importance of this figure. So if you have a figure like this, directly if you have the stress coming in a component, suppose it is somewhere here, that means my component is safe. If my stress coming in the component is somewhere here, then the component is not safe, it has to be redesigned. So this way we can explain the MSS theory or the maximum shear stress theory. Next we will see the distortion energy theory or the von Mises theory, which is also applied for ductile material, that is more relevant to ductile materials. So now we will come to the second criteria for failure. One is that is a distortion energy theory or von Mises-Henke theory. This states that the distortion energy theory predicts that yielding occurs when the distortion strain energy per unit volume reaches or exceeds the distortion strain energy per unit volume for yield in a simple tension or compression of the same material. So for this, now we should know what is distortion energy of the body. Now when a body is loaded by a force P, we know that stresses are generated in the body, and the stresses sigma on a suppose I have body here loaded by a force P. This generates a stress given by P by A and also generates a corresponding strain. Now the total strain energy of the component the strain energy per unit volume is defined as half into sigma into epsilon. This is the strain energy per unit volume of the body. Now the total strain energy in the body due to a loading given by this, for 3-dimensional loading like this case, the sigma 1, sigma 2 and sigma 3 are the stresses, consist of two components. One is called the hydrostatic part, where equal stress acts in all directions, equal stress of magnitude sigma AV. AV is nothing but average. This is called the hydrostatic part. Other strain energy is called the dilation strain energy, dilation energy of the body. And the remaining stress acts on the body, which is nothing but sigma 2 minus sigma AV, sigma 1 minus sigma AV, sigma 3 minus sigma AV, etc. This is called the distortion part. I'll call it distortion energy. That is the total strain energy consists of two parts. One is hydrostatic and one is distortion. That is, when you are giving a kind of stress to a body, it causes two kinds of phenomena. One is the dilation or volume expansion of the body, and another one is the shape change of the body. The shape change of the body is called the distortion, and this is the one which causes the failure. This dilation part of the hydrostatic part does not cause any failure. Here we can write sigma AV is nothing but sigma 1 plus sigma 2 plus sigma 3 by 3. That's the average of 3 stress. So this of the total strain energy, only the distortion part of the strain energy is causes the failure of the body, and the hydrostatic part does not contribute to the failure. So in this distortion energy theory, we are interested only in this term, the distortion energy of the body. So a given loading system like sigma 1, sigma 2, sigma 3, what is the distortion energy in the body? Now, as we have seen earlier, the strain energy of the body is given as half sigma epsilon. So when we have three principal stresses, sigma 1, sigma 2, sigma 3, we can write this as half sigma 1 epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 3. And we know that the strain sigma epsilon 1 is given by sigma 1 by E minus nu times sigma 2 plus sigma 3. Similarly for epsilon 2 and epsilon 3 also. So we can write epsilon 2 is nothing but sigma 2 by E minus mu by E into sigma 1 plus sigma 3, and epsilon 3 can be written as sigma 3 by E minus nu by E into sigma 1 plus sigma 2. When we substitute these values of strain in this equation, what we get is the total strain energy will be can be written as 1 by 2E into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. This will be the total strain energy. So this term we have found out what it is. Now we have to see what is the hydrostatic dilation energy. In hydrostatic dilation energy, what is happening? Sigma 1 is same as sigma 2, is same as sigma 3, is same as sigma AV. So for hydrostatic strain energy, I will write HSC. What we have to substitute is sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to sigma AV. So this in turn will give this as 3 by 2E into 1 minus 2 nu sigma AV square. And sigma AV we have already seen that it is epsilon 1 sigma 1 plus sigma 2 plus sigma 3. So this in turn will give it as 1 minus 2 nu by 6E into sigma 1 square plus sigma 2 square plus sigma 3 square plus 2 times sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. This is the hydrostatic strain energy, hydrostatic part or dilation energy, and this is the total strain energy. So what will be the distortion strain energy or distortion energy? We can say that distortion energy will be nothing but the total energy minus the hydrostatic strain energy. So this term minus this term will give the distortion energy of the body. So we have seen that the total strain energy is given as 1 by 2E into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu into sigma 1 sigma 2 plus sigma 1 sigma 3 plus sigma 2 sigma 3, and the hydrostatic strain energy is given as 1 minus 2 nu by 6E into sigma 1 square plus sigma 2 square plus sigma 3 square minus plus 2 sigma 1 sigma 2 plus sigma 1 sigma 3 plus sigma 2 sigma 3. Now the distortion energy is equal to total strain energy minus the hydrostatic strain energy, which will come out to be sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 1 minus sigma 3 whole square by 2 into 1 plus nu by 3 times E. This will be the distortion energy in the body. Now, what is the distortion energy for the tensile test specimen at yield? For tensile test specimen, we know that sigma 1 is equal to sigma 2 is not there and sigma 3 is not there. So this becomes, and sigma 1 will at yield point, sigma 1 will become sigma is equal to Sy, the strength of the material. That is the stress at the yield point. Stress at yield point is nothing but the yield strength of the material. So this becomes 1 plus nu by 3E into Sy square. So therefore we can say that yielding will occur when sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 1 minus sigma 3 whole square by 2 into 1 plus nu by 3E. When this becomes greater than or equal, that is equals or exceeds the distortion energy for tensile test specimen, 1 plus nu by 3E into Sy square. So this is the condition for yielding to take place. Now this we can write as sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus 1 minus sigma 3 whole square by 2 raised to half should be greater than equal to S1. This is the criteria for distortion energy theory. And when designing the components for this theory, we have to ensure that sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 1 minus sigma 3 whole square by 2 raised to half should be equal to Sy by N, where N is nothing but the factor of safety of the material. This is the condition for design of component based on the distortion energy theory. Now we will consider a element which is in a state of pure shear. So what will be the principal stress for a pure shear element? We have seen that for pure shear element, your sigma 1 will be tau xy, sigma 2 will be minus tau xy, sigma 3 will be 0. Or you can draw the Mohr circle as, this is the Mohr circle for the pure shear case. The first principal stress will be tau xy, second principal stress will be minus tau xy, and third principal stress will be 0. Now, so as per what will be the distortion energy criteria for this case? If you substitute this value, this condition, this set of sigma values, if you substitute in this equation, what do we get? We get it as tau xy square plus again tau xy square plus sigma 1 is tau xy, sigma 3 is minus tau xy. So this becomes 2 tau xy. So it becomes 4 tau xy square by 2. The square root of this should be equal to Sy. This is what 3 times tau xy, square root of 3 Sy is equal to Sy. And what is this? The shear stress at the yield is nothing but the Sy this into square root of 3 is equal to Sy, or we can say that Sy, that is the torsional yield strength or the shear yield strength should be equal to 1 by root 3 times of the yield strength of the material. Or distortion energy theory says that yield strength of the material, the shear yield strength of the material is equal to 0.577 of the yield strength of the material. In MSS theory, we saw that this is by distortion energy theory, and by MSS theory, that is my maximum shear stress theory, we saw that SSY is equal to 0.5 times Sy. So MSS is a very conservative theory. MSS is a very conservative failure criteria. Now we will see some application of this theories in the actual design process. Before dealing with the applications of the failure criteria, we will see some two more theories related to ductile materials. That is the maximum strain energy theory or the Higgs theory. The maximum strain energy theory predicts yielding of the material when the strain energy per unit volume of the material equals or exceeds the strain energy per unit volume of a tensile test specimen at yield. So what this says is the maximum strain energy in the material should not exceed the strain energy of a tensile test specimen. So what is this total strain energy? We have already seen earlier that the total strain energy is given as half of 1 by 2e of sigma 1 square plus sigma 3 square minus 2 nu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. This is the total strain energy of the body for a 3-dimensional loading system with principal stresses sigma 1, sigma 2 and sigma 3. So for a plane stress element, what will be that? For a plane stress element, you will have only sigma 1 and sigma 2 and sigma 3 becomes equal to 0. So for this case, plane stress element, we have sigma 1 square plus sigma 2 square plus minus 2 nu into sigma 1 sigma 2. So what will be the total strain energy for the tensile test specimen at yield? For tensile test specimen, we know that sigma 1 is equal to sigma 2 is equal to 0, sigma 3 is equal to 0, and at yield this sigma will become the yield strength of the material. So what will be the tensile test total strain energy for the tensile test specimen will be 1 by 2e into, in this equation put sigma 1 is equal to sigma, and sigma 2 and sigma 3 becomes equal to 0. So what does it give? It gives Sy square. Therefore, what is the failure criteria will be 1 by 2e into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu into sigma 1 sigma 2 plus sigma 1 sigma 2 sigma 3 plus sigma 1 sigma 3 should, when this exceeds, becomes equals or more than 1 by 2 into Sy square, the yielding will take place. Therefore, we can write this sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu into sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3 should always be less than Sy square. Now this we can take it a half here and we can cut it here. So this is the criteria for design of the component. Criteria that the material can withstand the load without failure. And when you go for design of the component, we have to include the factor of safety. That will be sigma 2 square plus sigma 3 square minus 2 nu into sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3, the square root of the entire thing should be equal to Sy by n. So n is the factor of safety. N is nothing but the factor of safety of the component. So this is how design is done for the maximum strain energy theory. So that is about the third theory, that's the maximum strain energy theory. Then we have one more theory, that is a ductile Coulomb theory. Ductile Coulomb theory is used for materials whose the strength in tension and compression are not equal. That is used for material whose strength in tension and compression are not equal. Or I can say Sy is not equal to Sc. For most of ductile materials, the yield strength in tension is same as yield strength in compression, almost same. So this theory does not have much of application. Only for few materials there is a small difference between the yield strength in tension and compression. But for brittle materials we can see that the yield strength in compression is 3 to 4 times higher than that in tension. That is, for ductile materials Sy is almost same as Sc. Brittle materials Sc is almost equal to 3 to 4 times Sy. So there also we have a brittle Coulomb theory. This ductile Coulomb theory is for the ductile materials whose yield strength in tension and compression are not same. So what this theory says is, if you have a body with three principal stresses, sigma 1, sigma 2 and sigma 3, similar to what we have seen in the maximum shear stress theory, maximum shear stress theory says that sigma 1 minus sigma e should be equal to Sy. But here what this says is sigma 1 by Sy minus sigma 3 by Sc equals 1. That is, if we take the example which we have seen in the MSS theory, we have seen that we have three stresses, sigma A and sigma B, and two stresses, sorry. We have sigma 1 is equal to sigma A, sigma 2 is equal to sigma B, and sigma 3 is equal to 0. Then we got the diagram like this, where this was Sy. Here the tensile strength and tension, the yield strength and tension and compression were same. So we got a polygon like this. Now for this case, in the ductile Coulomb theory, the tensile yield strength is not same as the compression strength. So here we have a modified diagram. For same case, the diagram becomes like this. This is yield strength in tension, and yield strength in compression is much higher, which we have already seen. Somewhere here. This is yield strength in compression, compressive yield strength. Here, this is a figure where Sy is not equal to Sc. So this is for the ductile Coulomb Moore theory. And when we do design of the component, we can say that sigma 1 by Sy minus sigma 3 by Sc is equal to 1 by N. This is the design of a component based on the ductile Coulomb Moore theory. With this, we complete the failure criteria for ductile materials. Now, before going to the failure criteria for brittle materials, we'll try to see the application of this failure criteria which we have studied till now by solving some examples.